pleasure to welcome Professor João Barros here in this school. He's so an active researcher that I need a piece of paper. Okay, he is a professor of electrical computer engineering at the University of Porto in Portugal. He is a founder of 2 startups and now a CEO of one of them, and also founding director of the Institute for Telecommunication in Porto, Portugal. He has been a principal investigator in numerous national European industry projects. And he is also co-author of a book. The book is outside. And his field of interest is large, broad. There's network information theory and security, with special focus on network coding, physical layer security, sensor network, transport network, and so on. João Barros has, including several other awards, 2 awards from IEEE, the Communication Society and the Research Award, and also the Consort and Information Theory Joint Paper Award in 2011. I would like also to say something personally. He has also a degree in flute, music, and my conjecture is that he can also play the piano very well, because like 4 years ago, I saw him teaching my daughter to play the piano. Welcome.
No, thank you so much, Simon. Well, thank you. It's fantastic to be here. It's my 3rd time at Unicamp. So the first time was like 13 years ago, which is really long, a really long time. But I'm thrilled, and it's great to see so many people from so many different places. So how many of you come from Latin America? Hands up. All right. And from Asia? All right. And from Europe? Wow. Anyone from Portugal? Ah, there you are. And North America? And Australia? New Zealand? All right, good. This is very impressive. And I'm going to talk today about physical layer security. And let me tell you a little bit how I bumped into this topic. And in fact, it may be interesting for you just to, as you look for your own research topics and as you decide on what you want to work and how you can have the greatest possible impact. For me, it has always been driven by 2 things. One is curiosity, and the second one is friendship. So wherever I found friends that I wanted to work with, I tried to learn what they were doing, and I bumped into all sorts of different problems along the way. And so with information theory, so my love affair with information theory started when I was an assistant in Munich with Professor Joachim Hagenauer at the time. So I was doing my PhD, and he asked me to teach information theory and source coding with him. And so I was basically initially doing tutorials, then I started doing some of the lectures, and I completely fell in love with the topic. And I was very fortunate because at the time in 1999, when I started my PhD, ISIT, so the big information theory conference, had a technical program committee meeting in Munich, and Professor Hagenauer basically asked me to help organize that. And so 3 months after I started my PhD, I found myself in a room with it was the time where technical program committees of conferences actually met in person to decide which papers would go published. And not now, but it's mostly online, which is very sad because people used to really have printed versions of the paper and discuss the paper in a room with all these people. And suddenly, lots of very well-known information theorists were in Munich, and I got to see also what a wonderful community this is. A community that, privileges intellectual debate and technical depth. And so I thought, yeah, I really want to work in information theory and do something there. So I started working on joint source channel coding at the time, because almost everyone in the lab was doing turbo codes, and I saw those bit error rate curves and the waterfall curves, and I thought, no, I don't want to look at waterfall curves my whole PhD, so I decided I want to go and do something that also has to do with the information and the nature of the information that you're coding. And so I started looking at source coding. And then eventually I finished my PhD with a thesis on sensor networks and information theory for sensor networks. And in Germany, when you submit your thesis and you go to defend your thesis, it takes like 7-8 months until you finally get to defend, a really long time. And so I thought, okay, I have some time now, so I want to learn something new so that I can use that as my next topic. And so I decided to take a course in quantum information and communication, which was taught at the physics department. And my assumption was, I'm going to go to 2-3 lectures and I'm not going to understand a thing, because I'm not a physicist, and quantum physics is probably not that easy, so I don't think, but I will try, and a lot of these things, you just have to just try and see what happens. And so I went to the physics department at the Ludwig Maximilian University in Munich for this course, and it turned out that the quantum information and communication course used a Nielsen-Schwann book, which is basically algebra, so it wasn't that complicated. And I started seeing all these interesting things in quantum cryptography that had to do with security, and it started getting intrigued. And I thought, why can't you just use this type of things also for classical channels and wireless channels? So why do you need, what exactly is so specific about the quantum phenomena that makes it possible to use, say, quantum cryptography effectively in optical communications, but would not make it possible in wireless? And so I was intrigued by this when I started applying for all sorts of universities, and I got interviews at Georgia Tech, and there I met Steve McLaughlin. And Steve McLaughlin was actually designing turbo codes and low density parity check codes for quantum cryptography. So he was improving the number of bits that you could generate, so secret bits for a key from a quantum channel using coding principles. And I thought, wow, this is really, really interesting and different, and security just seemed like a really, really interesting topic. So I started reading about cryptography and all sorts of things. And then I decided to go back to Portugal, because at the time Portugal was investing a lot in science and technology, and I wanted to be part of that. So I declined the invitation from Georgia Tech, and I went to Portugal, to the University of Porto. And I started my career actually in a computer science department. And my background is actually in electrical engineering. But there I met new friends from computer science who were doing, lambda calculus and all sorts of complex combinatorics. And so I started going more into discrete maths, and security just seemed like the right topic. And so I met Miguel Rodrigues, actually at ISIT in Australia. He's now a professor at University College London. And we started playing around with this notion of how to use information theoretic security in wireless. And that was my beginning of working in physical layer security. And I will show you throughout this lecture how you can actually build a security architecture that uses information theoretic principles to make information more secure. Eventually, Miguel and I had some theoretical results on wireless, on the secrecy capacity of wireless channels. And then I thought, now we understand better what the fundamental limits secure communication over wireless channels are like, but we don't have codes. We need codes. And that's when I remembered my conversations with Steve McLaughlin and also Andrew Tangaraj, who was his postdoc at the time. And so I called up Steve and Steve and told him, you know, we just found out this really nice property about wireless channels, and it looks like you can actually communicate securely over a wireless channel even when the eavesdropper has a better signal-to-noise ratio than the legitimate receivers. And he was intrigued, and then I asked him, well, can we use your codes that you are using for secret key distribution in quantum cryptography? Can we use them for wireless channels in a smart way based on these results that Miguel and I were able to prove? And that's when Steve said, you know, I have this brilliant PhD student called Mathieu Bloch, who has been doing the codes for quantum cryptography. You know, let me give your paper. So it wasn't published yet. But I gave him a preprint and said, let me give him the paper and see what he comes up with. You know, and a week later, Mathieu comes back and said we can use exactly the same codes, and this is how the protocol would look. And so within 1 week, he actually had the codes that we needed to bring that work to the next level. And so we started a long-term collaboration. Mathieu came to visit me in Porto. He eventually graduated. He was my postdoc for a short period of time. Then he became a professor at Georgia Tech. And then we wrote the physical layer security book together. And again, it was very much driven by friendship. And in fact, Mathieu is the godfather of my youngest son. So a lot of this work is very closely connected to, you know, lots of very, very special moments with really great, fantastic people. And so that is a very important driver. You know, being a researcher is pretty tough because you have to deal with all this uncertainty. Actually, being an entrepreneur is not that different, actually. There's just a huge uncertainty. And so you kind of need this network of people that share this burden with you and that you can also celebrate with when you really achieve great things. And so I wanted to give you this introduction because I also feel that very often, you know, the decisions are based on how many papers am I going to publish if I work in this area, or what will this bring to my career for the next step. But I think an even more important question is, how can I create around me a support system that ensures that I'm constantly being challenged intellectually, that I have people that I can really share all this excitement and all this work with someone, and how can I, you know, also contribute to other people's success and happiness, and then eventually I believe that all comes back to you again. Okay, so physical layer security. When you look, you know, actually when you talk with end users and people, and when you talk to them about the internet, typically, you know, what people, it's just blocked, let me see. All right, so my Mac is giving up. So I should just continue with personal stories and anecdotes. All right, so let me see, I have to see what's going on. So I'll just restart the PowerPoint, probably, yeah. Sorry about this, just 1 second. I think I have way too many applications on. Okay, so this should work now. Let's see. We're still there? Yeah? Okay. All right, and here we go. So when you talk to people, and by the way, also, I think it's really important to talk with the end users and see how they look at the and what we do, information communication technology, typically they see the edge of the internet. So they see all sorts of applications and computers and more mobile, but they don't imagine, often that behind that network is like a really, really complex system with all these different entities that own different parts of the hardware and this wireless edge, which is becoming larger and larger and with more and more different kinds of things and moving things connected to it. And security, is a huge issue because it deals with trusting these different elements in the network to do what you expect them to do, and trust the people that actually administer and have access to resources in the network to actually do what they're supposed to do. And so it has an enormous relevance because without trust, the internet doesn't work, and trust is not possible without sound security engineering. And now, when you look at how the architecture for the internet is built and how the different protocols work together, you find a layered architecture, which I'm sure most of you have seen before, where essentially, you have at the physical layer the ability to turn, bits of information into signals that you can send reliably over a noisy channel, and use channel coding, modulation, and other tools to do that. At the link layer, you basically solve the problem of who gets to access the channel at different points in time. Then at the network layer, you solve the problem of how to get one packet from one end of the network to the other and how to route that packet. Then you have the transport layer, where basically you look at how to ensure that the network is not completely congested. I actually find it a miracle that in the internet, all these different devices with TCP actually exert a form of distributed self-control that avoids the network from collapsing. It's actually comparable to having a traffic system in a city without any traffic lights, and yet there's never congestion. So part of it has to do with the fact that many networks are over-provisioned, so we actually have in many places more capacity, especially on the fiber, than we actually need. But it also has to do with the nice way in which TCP/IP was actually developed. And then finally, you have programs and applications and processes and so on. And this architecture developed, from the old ARPA network in the 60s and 70s, and then eventually becoming our internet, and uses this divide and conquer principle, where basically you have to face a complex problem of how to make a large network of networks work, and you just divide it into these different layers and different steps. Now, one thing that becomes very clear when you look at that architecture is that one really important thing is missing. What is missing? Security. So none of these layers actually deal with security, and this has some historic reasons. Is that initially the computers who were connected were in premises, so they were physically secure, and they were heavily controlled, and there wasn't much knowledge in society about computers in general, and there wasn't much interest in attacking those systems. This changed completely with the personal computer, and when all these computers were connected to the internet, and you started having e-commerce applications, then suddenly, security became tremendously important. And so the question of where do we put security became really important. And so when you look at the security architecture, it's basically a patchwork of cryptographic schemes and primitives that are put at the various layers. So you have admission control, like for the wireless with the passwords and so on. You have virtual private networks at the network layer, where you do like IPsec, a tunnel that through multiple encryption layers allows you to establish a secure end-to-end connection and with authentication. You have secure sockets layer at the transport layer for pretty much the same thing, and then you have end-to-end cryptography application. And sometimes you have all of them at the same time. For example, when you are accessing your bank account, you have end-to-end cryptography, but then typically you're using HTTPS, which uses SSL, and so on. And very often you are doing multiple layers of authentication and multiple layers of cryptography. And this doesn't mean that the system is more secure, because very often the attacks actually come, from hacks either on the software, on the security software, or hacks on the protocols and flaws that have to do with the messages that the protocols exchange. And so there are all sorts of attacks, and it's really an arms race because you have a real industry of attacking systems, and typical models are based on denial of service and extortion, where you basically just block a server and ask for money to be able to free that. And from this type of models to other more elaborate attacks that involve fraud in banking and financial transactions. But so this is a huge topic that is very, very far from being solved. And of course, it's very hard to think, okay, we're going to do a clean slate architecture now where we think from security right from the beginning. You can do that as a research project, but it's very hard to implement that in practice, given the advanced state in which the internet is already. But when you look at the architecture, you see that there's one layer that was pretty much ignored in security solutions up until recently, which is the physical layer. So besides, using spread spectrum codes that, especially for the military, were mostly targeted against jamming attacks, there was very little at the physical layer that was actually done to protect the signals themselves. And there are many reasons for that, and we'll talk about this in a minute. But why do we care? So why do we care about physical layer security, right? If we're able to do end-to-end security here, then it doesn't really matter, right? Because everything is secure over here. Well, the problem is that these protocols use basically public key cryptography, which is one drawback, and we'll see soon what that drawback is. And then the other aspect with the architecture is that it's not very simple to implement many of these algorithms in devices that have memory constraints and processing constraints. And so especially as you have more and more mobile devices and more things connected, you have to be able to secure those things with primitives that are simple to implement and can be run in very, very basic systems. And the current security architecture is just too heavy for many of those devices. But the main reason why we care about physical layer security, in my view, is that the internet is becoming mobile, and so more and more wireless. And so, as you see, the mobile data is growing dramatically and is actually continuing to go even beyond in latest projections. And so you really have to care about the security of wireless systems, and a lot of it has to do with securing the wireless link, which of course is very different from securing a cable, especially if the cable is underground, like in a fiber optical network. Now going back to Shannon, and I love this picture because every time I see this picture, it seems like Shannon is looking at me and saying, "Are you doing anything relevant today?" So it's a good picture to keep in your desktop on the computer. It just reminds you. But the second reason I really like this picture is that if you take away Shannon, you actually see how he thought, and engineers and information theorists think a lot in terms of block diagrams. And I do find that also a difference as opposed to computer scientists. Having worked in a computer science department for 4 years, a lot of our electrical engineering is about thinking about systems and electronic circuits in your mind. And so you've talked extensively about the basic model for a communication system introduced by Shannon, but he also introduced really relevant models for security. And this was in another paper, not the famous one, the communication theory of secrecy systems, that is probably the most cited, or one of the most cited papers in history, but also this other paper, communication theory of secrecy systems, where he says, the problems of cryptography and secrecy systems furnish an interesting application of communication theory. So it's interesting because the way he wrote this introduction, basically, his work on information theoretic security is just an application of the theory that he had developed before. And so he says in this paper, a theory of secrecy systems is developed. The approach is on a theoretical level and is intended to complement the treatment found in standards works on cryptography. And at the time, cryptography was not really a science. So this is in 1949, and actually the work was developed before. We'll see in the next slide. And basically, at the time, cryptography was a little bit more like cooking. Okay? You take a little bit of this, a little bit of that, you put it together in a cipher, then you do all these attacks and you prove, certain properties on the ciphers, but there wasn't a really fundamental work about the nature of cryptography. There's nothing wrong with cooking, and there's nothing wrong with hacking, but Shannon wanted to understand the fundamentals. And so he says, there are detailed studies made of the many standard types of codes and ciphers and of the ways of breaking them. We will be more concerned with the general mathematical structure and properties of secrecy systems. Okay, so the fundamentals of those systems. And I always love it because he immediately writes about the limitations of his work. So there's really no hype. It's like the treatment is limited in certain ways, and then he goes on to limit it, how his study is limited. And then when you go to the last page, you find this really interesting note, actually the next page, which is the note over here, which says the material in this paper appeared in a confidential report in mathematical theory of cryptography dated September 1, 1946. So that was a year before, which has now been declassified. Okay, so he was working on this during World War II and with the military, and so it was classified, and he could only publish it later. Okay, so when you look at the fundamentals, so how would you formulate the problem of security? So typically, you have a sender and a receiver, which in tradition has been called Alice and Bob, and typically the problem of communication would be simply to reproduce message W sent by Alice in a remote location where Bob is receiving that message. And so you want to reproduce W at a remote location where Bob is. Okay, that would be the problem of communication. Secure communication just adds one more constraint, is that you want this message to be recovered at a remote location by Bob and nobody else. Okay, so that's the additional restriction, is that nobody else should be able to recover that message. Okay. And if you have a channel with no errors, where basically everyone just gets whatever Alice sends, really the only way to do this is to encrypt the message. And what that means is that you are going to share a secret key between Alice and Bob. And so you want X to be a function of the message and of the key in such a way that Eve is not able to recover the message W if it doesn't have the key K. And Bob is able to recover it without errors by using the key to decrypt the cryptogram. So X is the cryptogram, W is the message, and you have the key K. And so computational security basically assumes that there are algorithms that generate the cryptogram as a function of the message and of the key, which guarantee that at least in useful time, whatever that is, Eve is not able to crack that algorithm. Okay, and so you take certain functions that you assume are intractable, or so cannot be solved in useful time, and you use them to protect the message, or at least to share a secret key. And so many of these assumptions are unproven. When you deal with public key cryptography, you see that this notion of one-way function, which is a function that, and one-way trapdoor, which are terms that basically describe this sort of function that cannot be reversed by Eve unless she has a key, are based on the notion of tractability that implies looking at the complexity, the algorithm complexity of the functions that Eve has to use to be able to solve the puzzle that delivers the message W. Today there are already theoretical results that show that quantum computers, so computers that are based on quantum mechanics and not classical mechanics, that those computers are actually able to crack those algorithms. So we have the software, but we don't have yet the hardware. At least we don't know yet of an implementation of quantum computers that actually is able to process, for example, large integers and factor them in such a way that you could actually crack public key cryptography. But anyways, when we say unproven assumption, it means that based on the type of computing machines that we have today, the algorithms are secure, and our entire economy is based on that right now. So public key cryptography is used extensively on the internet, but it could be that the simple invention and implementation of a quantum computer just brings down this entire security architecture the way it is now. And typically this is done at the upper layers of the protocol stack, as I was describing before. But there is this other notion of security, which Shannon introduced in his paper, which is information theoretic security, also called perfect security or unconditional security. It depends on how much you like this concept. But basically the notion of perfect security is a notion that doesn't put any constraints on any assumption on the computational capability of the attacker. So whereas here we are saying that Eve does not have enough computational power to be able to solve certain mathematical puzzles that are required to be able to recover the message W from the cryptogram, here we are saying that Eve can have all the computational power in the world, including a quantum computer, and the system is still secure. And so basically what we're saying is that when I have to guess the message based on what Eve knows, actually the best that I can do is just to use the probability distribution of the message, which means that essentially the cryptogram doesn't decrease my uncertainty or my entropy about the message that was sent, or in other words, and by now you know how to manipulate these expressions, so if I basically subtract h of w on both sides of this equation, then I get that the mutual information between the cryptogram and the message is 0. So basically I'm generating a function that has nothing about the message w. And there is a cipher that achieves this, and it's called the one-time pad. Who has heard about the one-time pad before? Okay, almost everyone has heard about the one-time pad. But if you have heard it, then you can tell me how to actually do it, for those of you who haven't heard it before. And so essentially, basically, I'm going to take one symbol of my message, and I'm going to do an XOR with one symbol of my key, and that generates the cryptogram X. So if I have a binary message, and I have 0, 1, I'm not going to put this, otherwise I'm going to have to cross all the zeros. So 0, 0, 1, 1, 0, 1, 0, 1, 1, 1. Okay? So basically, this is the result of my random number generator in my brain. And now I have, a key. And so I can switch on the random number generator again. And I just have 1, 0, 1, 1, 1, 0, 0, 1, 0, 1. Okay? And so now what do I do to generate the cryptogram? Do a symbol by symbol XOR. Right? And so I go, hi Swelly. I haven't seen Swelly yet. Okay, 1 and 1, 0. 1, 0, 0, 1, 1, 0, 0, 1, 1, 1. Okay? And that's my cryptogram. Okay. So now if Eve gets this cryptogram, since this key is Bernoulli 1/2 sequence, so it was generated from uniformly distributed random process. So now Eve really has no idea what the key looks like, and the best that she can do is just guess, okay? And so there's really the mutual information between X and W is truly 0. Bob can just, take the key again and do what? Loud? Just do the XOR again, okay? 0, 1, 1, 1, 0, 1, 0, 1, 1, 0, 1, 0. Okay? And just recovers W again with 0 error. Okay? So to convince yourself that this is really information theoretic secure, what you need to think is that to do an XOR, symbol by symbol with a random 1/2 is exactly the same as sending so it's 0 and 1, 0 and 1, sending the message through a binary symmetric channel where the probability is 1/2, 1/2, 1/2. Okay? So it's exactly the same thing for a one-time path. And so what is the capacity of this channel? 0. Okay? So again, the best that Eve can do is just guess. All right. Good. So problem solved. We have a very simple cipher that we can use in all the systems. So why do we need public key cryptography and computational security and all that? Yes?
Cipher, exactly.
No, he was first, so we have to be disciplined.
As long as the message size increases, you need a huge key, an infinite key.
Right. So I just generate a random bit for every bit of information.
It will be periodic at some point.
Hmm?
It will be periodic at some point.
Yeah, the random part is a big problem.
No, I can just use a random number generated that is not based on a shift register. I can just use. For example, there's a company that actually sells a quantum-based random number generator that gives you, truly random. So how can what? So the question is, how do we distribute this key? Because my problem was if I have like 1 terabyte of data to send now, and I had to send it over a channel from Alice to Bob, or even just 1 gigabyte of data. Now I have to generate a key, which is how long? Exactly as long as the message. And so I have to share that key. So how do I share that key securely? It's a problem, right? So that's the problem. Well, I can do like the United States and Russia during the Cold War, which is I send army generals with little, suitcases that share secret keys between the Kremlin and the White House. So this actually happened, and today the military still exchange keys in suitcases that are guarded by 3 keys held by 3 different people and all that. Okay, but it's very hard to do. To buy things at Amazon with suitcases that have secret keys, right? So we have to find a way to solve that. And so the one-time pad is a beautiful construct, but for a long time people just said, okay, it's a beautiful theory, it has no use in practice. And then in the 60s when the public key cryptography came up, it was a miracle because now you could actually do it basically secret key exchange and be able to do authentication and all sorts of applications with keys that were much smaller and were computationally secure. You couldn't really break them. And so information theoretic security was forgotten for a pretty long time. There are a few papers here and there, but nothing that would make it mainstream in any way. And so the main questions were what are the fundamental security limits at the physical layer? Those are things that are that interest researchers. Then which notions of security are we talking about is really important. So the difference between computational security and information theoretic security was debated and still is. And what is strong secrecy and weak secrecy? than whether this is practical at all. So I would dare say that the majority of security experts in the world still thinks that information theoretic security is a nice theory, but that's it. What kind of code constructions can we use? So we'll talk a little bit about that. And how do we build protocols based on information theoretic security? So these are other questions that are important. And can we combine physical layer security and classical cryptography in what ways? And how can we secure new wireless networking paradigms like network coding and other things that you've been talking about in this course, okay? So much more of my work has been around these questions in various ways. We go more from, theory to practice. So once you understand the fundamental limits, you need codes to be able to achieve them, exactly like in pure or basic communications problems. You need to do that for security as well. And basically these are the more architectural things, which is if you have a physical layer that is secure, how does this affect the protocols that you basically have on top of that in the rest of the architecture? And then can we combine physical layer security with classical cryptography? This is mostly motivated by computational issues. So and the basic question there is that if we have a physical layer that is more secure, that ensures, for example, that if you send a cryptogram, then Eve always has a noisy cryptogram. And so the first question is, if you can ensure that she always has a noisy cryptogram, is it more difficult to decrypt a noisy cryptogram or a clean cryptogram without noise? And so you would assume that the noisy cryptogram is more difficult to decrypt, but this requires proof. Okay, and so in the second, if it is more difficult to decrypt, does this mean that we can reduce the complexity of the cryptography because we have a more secure physical layer? And so this is another interesting open problem. So there are still many, many, many open problems. I will walk you through some of these and basically from the theoretical foundation, so the fundamentals of information theoretic security. We'll talk about strong secrecy versus weak secrecy and what this means. This is really important. For me, this is one example of how theoreticians can go in a direction that is very misleading when you lose sight of what the engineering problem is that you want to solve. And so this is an interesting discussion also for someone who is starting a scientific career, is just to understand, where is the fine line, between theoretical depth or technical depth and practical relevance, and where you want to be in this whole space. And then secrecy, capacity of noisy channels. I'll talk a little bit about our own work in there. And we'll show examples. I won't go too deep into this, but show examples of how to combine cryptography and coding, secrecy capacity achieving codes, and how to do secret key agreement. And so the beauty is that if you're able to do secret key agreement and you share a secret, then you can use cryptography. But you solve one important initial step, which is how to actually get a key that is secret. And then we'll talk a little bit about multi-user secrecy, how attacks on physical layer security systems are different, and we'll look a little bit at what happens with very large networks. So let's see how much we can cover. So going back to this model, if you look at it, it's actually a bit pessimistic. Why is this model pessimistic? So we concluded from this model that there is a cipher called the one-time pad, that requires 1 bit of secret key for every bit of the message, and so it's impractical for most systems. But when you look at this, I would say this is a pessimistic system. Why?
Because Bob and Eve receive the same signal.
So because Bob and Eve receive exactly the same, and why do they receive the same message? That's correct.
Because you don't assume there's noise.
Because it doesn't assume that, or it assumes that there's no noise in the channel. And so it's pessimistic because typical channels do have noise, right? And so it's a worst case assumption, and that is the worst case assumption that Eve receives a cryptogram, that is identical to the one that was sent by Alice. Now you could argue that if I design a system that is secure under this assumption, then it's going to be secure, over any channel that introduces noise. And that for a long time was the argument. But if that assumption then results in systems that are too complex to be implemented, or that rely on unproven mathematical assumptions, then you may want to revise that model and rethink, okay, so what would a model look like that has noise? And that's what Weiner did that already in 1975, but around that time, the world became obsessed with public key cryptography, and so this was largely ignored. But basically, the idea is that you have a broadcast channel. So Alice is sending a message, and what Eve sees is actually a noisy version of what Bob sees. And so there's noise, there's a channel described by P of Y given X between Alice and Bob, and then there's a degraded version to Eve. Okay, and so this is a degraded broadcast channel, and we put two constraints. So one is we want reliable communication, which means that the probability of error should be arbitrarily small for Bob, and we want at the same time that the mutual information between the message and whatever signals Eve is able to see, also goes to zero asymptotically. And there is a problem with this definition of security, which we'll address in a minute. This is what today we call weak secrecy. And the problem has to do here with this normalizations, that we're actually computing the mutual information per symbol, but averaged over entire blocks. And that's a problem, as we see later. But so we then define the secrecy capacity basically at the largest transmission rate that you can achieve while satisfying both these conditions. So reliable communication with Bob and arbitrarily small leakage to Eve. What Weiner showed is that in the degraded case, so when you have Eve with more noise than Bob, then the secrecy capacity is strictly positive. So that means I can transmit at a certain rate with information theoretic security over a channel like this. Or in other words, there exist codes that allow me to achieve arbitrarily small probability of error between Alice and Bob, and mutual information arbitrarily close to zero as n becomes very, very large. Okay. Now, when you look at this result, you actually get a nice range, and you have a rate region that is basically describes all the operating points that are possible in a system like this. So, for example, if I wanted to transmit at the capacity of the main channel, which is so the capacity between Alice and Bob, okay, then Eve will get a certain number of bits from my message. Okay, let's call it D. And so the entropy is not the uncertainty of the message; it's lower than that. It's this point over here. But Weiner showed that there exists a positive secrecy capacity where actually, my uncertainty is arbitrarily close to the entropy of the message. So I have this point here. And so this whole region is actually achievable. So there exist codes that achieve these operating points inside of this rate region. Yes?
What's very strange about this figure is that we are increasing the transmission rate, and until CS we have the equivocation a constant.
Right. No, it's not. So it's not. Let me tell you why it's not strange. It's not strange because this is the maximum rate at which I can transmit that ensures me perfect secrecy. I can transmit at lower rates, and I still satisfy that. Right? It would be strange if it continued this rate, but this way it's not. It's the same thing as saying, okay, up to the capacity I can transmit with arbitrarily small probability of error. Okay, it's the same principle. Okay. All right. But then, of course, the result is based on typical sequences and random coding and so on, just like the channel coding theorem. So it doesn't tell me how to construct those codes. And so that was one problem with this result, was that I didn't have codes. But even worse than that was to say, okay, Eve always has more noise. And so when you think in practice, what are real systems where I can assume that Eve has more noise? And there aren't that many. So that was basically the conclusion when people thought about using the wiretap channel in practice. Now, how do you prove this result? So basically, instead of using just a codebook that assigns one code word to each message in the message set, you actually assign multiple code words to each message. And basically what you do, Alice does, is that out of all possible messages for that, or out of all possible code words for that particular message, she just chooses one randomly and sends it. And now because Bob has a higher capacity, so she has less noise, she's able to identify exactly which code word was sent. Eve basically is left with the set of possible messages that are all equally likely, and so in fact the distribution is the same as the distribution of the message set. And so she's not able to infer anything from what she sees, simply because she doesn't have enough correct bits to be able to find the code word. And for her, it's just a larger blur. And we'll see how to construct these codes probably in the next lecture, not in this one. But basically, the proof relies on the fact that Eve has a smaller capacity than Bob, and so you construct the codes in a way that exhausts capacity, so you are above capacity for Eve, and she's not able to decode, and you're below Bob's capacity, so he's able to decode with arbitrarily small probability of error. And then for the converse, you use Fano's inequality, and it's just another example of those long sequences of information theoretic inequalities. And so here's an example of a system that satisfies Weiner's conditions. So the signal-to-noise ratio between Alice and Bob, well, in this case, Bob and Bob, and not Bob and Bob and Tim, is smaller, than the signal-to-noise ratio between me and them. So if I'm here and you're not able to. So this is from Get Smart, from this series. You're way too young to actually know. But basically, this is an example of a system like that. Okay. Now, how do you go from a degraded broadcast channel to a general broadcast channel? And so, which means that they're actually talking in all directions. Well, you use a broadcast channel. Okay, and how do you do that? Well, basically now, instead of having P of y given x and then P of z given y, you just take a general probability distribution P of y z given x, and you don't factor it into those marginals. And so Imre Chisar and Janusz Kerner in 1978, studied this problem and basically realized that you still need to have what they called, a less noisy channel between Alice and Bob than between Alice and Eve. And so the capacity is only positive when the mutual information between x and y is larger than x and z, which is not very different from the previous one. But you actually characterize the secrecy capacity in terms of this auxiliary random variable u over here. And so it's not very encouraging. You think, okay, so in a general broadcast channel, Eve still has to have more noise for the system to work. Okay. More recently, we actually have scenarios where you can assume that, or you do assume that the attacker has more noise than the legitimate parties. And so this is the webpage of the NFC forum. Who doesn't know what NFC stands for? So near field communications. So these devices, actually mine is charging, so that's why I know it's here. So these devices, some of them now come with NFC, which is basic technology that is very high rate, very close range, which means that you can do payments and all sorts of things with that and share photographs and so on. And so when you look at this consortium, which includes companies like Sony and NXP and NEC and Nokia and Visa, so the guys who manage our credit cards, okay, this is what they say about security. So I'll make it a little bit bigger so that you can read. So they say, because the transmission range is so short, NFC-enabled transactions are inherently secure. So see, you don't need to do anything. If they're close, so they're already automatically secure. And they say another important, interesting thing. They say also, physical proximity of the device to the reader gives users the reassurance of being in control of the process. I love this sentence. Because it really shows that security, is about trust, right? About reassurance of being in control of the process. So the algorithm itself. So this is Visa, okay? Visa telling you, Microsoft is telling you, the MasterCard. Oh my God, all right? Okay, so this is a situation where you would assume that the eavesdropper is further away, okay? But you can still use some nice solutions and codes to make NFC stronger. Right now, they just use a very simple, actually, physical layer, okay? Okay, so how could you do this for wireless channels? And so that's what I started thinking about around 2005. And basically the model is very simple. You assume that you have a wireless channel between Alice and Bob and a wireless channel between Alice and Eve, and you start doing the math and figuring out what happens. So Shannon fortunately left us with some results for the Gaussian channel as well, and lots of people have done brilliant work on actually extending that to all sorts of wireless channels that go way beyond Gaussian. But in 2008, we had the information theory workshop was in Porto, and we actually have a world record, which is the largest Shannon formula in the world. So this was in the Palácio da Bolsa, and that's the the Shannon capacity for the Gaussian channel. And so when you have a scenario like this, like the one in this room, where you have a Wi-Fi router and you have all these different laptops connected to it, so essentially, basically, what you have is wireless channels that have Gaussian noise and fading, which means that the signal-to-noise ratio is going to vary depending on the fading profile of your channel. And this is true for Eve as well. And I remember actually when Miguel and I were discussing about this, and then I started drawing this on the board, and then we had one of these aha moments, which is, there are moments, even if on average the signal-to-noise ratio of Eve is higher than Bob's, there are moments where Bob actually has a signal-to-noise ratio that is higher than Eve. Okay, so it's not true always, and that was the key observation. And then the question is, can we exploit this, and how can we exploit that? Okay, so that was the key idea here. And so to be able to analyze this, so essentially you have the message and the code word, and you have multiplicative fading coefficients, and you have Gaussian noise, and the same thing for Eve. And it's you assume that the fading coefficients are independent, but basically this is a broadcast channel. And we assume that the fading is quasi-static, so the fading coefficient stays constant over the transmission of an entire code word. And then there are some assumptions on the distribution of the coding coefficients. And so when you do that, what do you want? You want to maximize the transmission rate between Alice and Bob, and you want to minimize the leakage. And a few years later, Mathieu Bloch and I also proved this result for strong secrecy, and I'll show you the difference in a second. But so basically, the secrecy capacity will then be defined exactly as with Weiners. So the maximum transmission rate are where you can minimize the information rate to Eve. Okay, and so this note is important, which is in 2000, Maurer and Wolf actually showed that this is a very bad secrecy condition. And there's a better one, the strong secrecy condition, where basically you do not normalize. So you look at the mutual information actually symbol by symbol and not averaged over an entire block. Okay, and so we will see in a second how we did it. But basically, we just proved the result again in 2008 for strong secrecy. And so the first way to think about it is that since the fading is changing, you can define, the mutual information across, a certain time where you actually have stable signal-to-noise ratios for Alice and Eve. And so you can compute the capacity, over a certain period of time where your fading coefficients don't change. And then you can look at what is the probability that that secrecy capacity is going to be 0 or positive depending on the distribution of your fading coefficients. And so that's basically what we did. We defined the outage probability, which is the probability that I set a certain target rate at which I want to communicate securely, and the secrecy capacity that I have at that time is smaller than the target secrecy rate that I am sending. Of course, if I knew beforehand how the channel would look like, then I would only transmit when I have a positive secrecy capacity. Okay, but since I don't know, I just have to decide, okay, I will transmit at a certain threshold, and this allows me to quantify exactly how many bits I'm leaking when I decide to transmit at a certain rate. Okay, and so you do some maths, and you actually get an expression for the outage probability of outage secrecy capacity that basically depends only on the signal-to-noise ratio between Alice and Bob, your target secrecy rate, and the signal-to-noise ratio between Alice and Eve. Okay, just 3 parameters. And so you can then plot them, and you can see what happens as you vary the quality of the channel between Alice and Bob, and you vary the quality of the channel between Alice and Eve. Then you can actually quantify it and see what is your outage probability and vary. You could also, for a certain target secrecy rate, you can also translate the signal-to-noise ratio into distance, and this is basically asking, so what is my secrecy capacity when I'm doing near-field communications and the eavesdropper is like 10 meters or 100 meters away? And so you're actually able to quantify also what your outage probability is going to be. And you want it, of course, to be as low as possible, which means that your eavesdropper has to be as far away as possible. That's basically the outcome here. Okay. Then you can turn it around, and instead of outage probability, have actually the outage capacity. And so this is the throughput that you get, the secure throughput that you get, again, for these different parameters. And so again, you vary the signal-to-noise ratio of the channel between Alice and Bob, and you parameterize the signal-to-noise ratio of the channel between Alice and Eve. And the interesting thing here is that you see that when you don't have fading, and here we are comparing fading and non-fading, so the thicker lines are the Gaussian case, and the thinner lines are the fading case, and then you actually see, that your secrecy capacity with fading, okay, is higher than your capacity. So this, for example, this is the capacity without fading, and this is the capacity with fading. And so fading actually helps security because of that phenomenon that we described before. Okay, and so that was the big surprise, was that when you compare the throughput, the secure throughput that you get for the Gaussian case and for the fading case, then in the Gaussian case, you only get positive secure throughput when the signal-to-noise ratio between Bob and Alice is larger than the signal-to-noise ratio between Eve and Alice, which are these curves over here. But with fading, even before that, you already have a positive secure throughput. Okay, and so that was the big insight from that paper, was just to realize that when you have a wireless channel, then you may actually be able to communicate securely even when Eve has a better signal-to-noise ratio than Bob on average. Okay, on average.
Sorry.
Yes.
Why does the outage of secrecy outage make sense? Because what kind of application doesn't mind being compromised for 10% of the time?
So very good point. And so here is the from an architectural and engineering perspective, here is the argument. What this ensures is that Eve will get a noisy cryptogram. And so I would never use physical layer security alone.
So you concatenate it with another thing.
But I use it as an important building block of a security architecture that allows me, for example, to reduce the complexity of cryptography in the upper layers, because I have a physical layer that is more secure than a noiseless channel. Okay, so this allows me to control, to some extent, what is the error rate that Eve is going to have on average, and that's why the outage probability is useful. But it doesn't give me perfect security.
What's the difference of using a normal code? Because if you use a normal code, Eve cannot decode at any. I mean, look at it independently.
No, it's not true. So if you use a normal code and Eve has a better signal-to-noise ratio than Bob, then it's able to decode.
But right now it can decode too, right? But you consider it as an outage.
Yes, but the point is, indeed, but the point is that I can quantify how, I can control and I can quantify how many bits Eve is actually able to decode. And that makes a difference when you're then designing cryptographic schemes on top of that. Yeah. So let's talk a little bit about the notions of security. So as I mentioned before, weak secrecy, which is what we were using, is that, so let's imagine that this, so UN is my source sequence or my message sequence. Next n is the cryptogram. And so what I'm saying here is that when I take, a block of message symbols and the cryptogram, then on average, my uncertainty about the message given the cryptograph symbol, has to be arbitrarily close to 1. Okay? You can also define this in a stronger sense by saying not on average, but actually the entire block has to be, so my uncertainty about n bits given n bits of the cryptogram has to be arbitrarily close to n. So what is the difference is that here I may actually have 1 bit where my uncertainty is actually very close to 0, but on average I am close to 1, whereas here I am forcing each and every symbol, to have an uncertainty at Eve arbitrarily close to 1. And so is it clear why this is stronger than this? Okay, so this makes all the difference when you look at secrecy systems, okay? Because initially Weiner used this, and so we only had the result for this secrecy capacity. So Maurer and Wolf in 2000 actually showed that when you substitute this criteria and this criteria, for this criteria, you actually get the same result. Okay, so this doesn't change the result for the discrete wiretap channel, but they didn't prove it for any of the other channels. Okay, and so this was known in 2000, and when people started becoming excited about information theoretic security again in 2007, 2008, and so on, at some point in 2008, I read this paper again, and most information theorists, don't like this paper very much because it's basically a cryptography, computer science paper. It uses expanders and all sorts of mathematical techniques that are used in theoretical computer science, but are not very, or until then were not very common to be used by electrical engineers in information theory. And so that paper was ignored, but I wasn't happy with having results that were based on something that was obviously wrong. And so people weren't, I'm sorry, I said expanders, so extractors, not expanders. But so people continued using this, this criterion, and I had many discussions with colleagues about this. And so Mathieu and I decided, okay, the only way that we can show that it is wrong to use this is actually to prove it for the Gaussian channel. But let me show you through a simple example why this criterion is really not a good idea. So suppose that I have n bits of binary data that I want to encrypt, and I'm going to use a one-time pad just like over there. But you know, I don't have n random bits. I only have n minus k random bits. So my cipher is very simple. I'm going to use this n minus k bits and just compress this first part. And then the rest I'm going to just leave it the way it is. Okay? Is this a good cipher? No, is this a good cipher for perfect secrecy? No. Okay, so it's clearly not perfect secrecy. Okay, so let's look at our criterion. So remember the difference between these two criteria. So assume we are using this encryption algorithm, and let's compute the weak secrecy condition. Okay, so we are going to, what are we going to do? 1 over n, the entropy of un given xn. Okay, which in this case, what is my uncertainty about the message sequence given xn?
N minus k.
So it's the n minus k bits, right, that are protected by a one-time pad. So it's 1 over n minus k, which means that I have 1 minus k over n, and this has to be greater than 1 minus epsilon. Okay, so this means, you know, as n becomes big, the number of bits that I'm leaking, okay, also can become, you know, as big as I want. As long as it grows sublinearly with n, I am actually leaking an unbounded number of bits, and I still satisfy the weak secrecy condition. Okay? So if I do my math based on this condition, I am actually accepting that I may be leaking an unbounded number of bits. It just needs to grow a little bit slower than n, but not much. Okay, so this is a problem. But when you look at this does not satisfy strong secrecy, right? Because the uncertainty about un given xn is n minus k, and this is not equal to epsilon. So if k is close to n, it won't be epsilon. So I'm actually limiting, you know, this thing over here. Okay. All right, so we published a paper in 2008 that had this example, and it had the results for the Gauss. Actually, this example is a variation of an example that was already in Mara and Wolf's paper. And still, people continue to publish, and now there are thousands of papers about information static security using weak secrecy. And I got really upset. And I went and I talked with many of our colleagues, and basically I heard different types of arguments. One was, oh, but Weiner did it with weak secrecy, so why shouldn't we do it with weak secrecy? So that's one of the things that we have to be very careful about our community, is that we tend to worship our information theory gods, starting with Shannon and then, you know, Gallagher and all the other. And we have to be careful in science in general with worshiping our gods, because sometimes our gods are wrong. Okay, and so we have to be able to correct things. And there's nothing wrong. Nothing diminishes Weiner's work because he had a weak secrecy condition. And Mara and Wolf just published a paper and fixed it, because just the idea of having noisy channels for cryptography is just beautiful. And so that contribution alone is already huge. So we're not saying bad things about Weiner simply because that little technicality was not correct. But the only way to improve and keep expanding our knowledge is to be able to accept what are the flaws of previous work and correct it, while honoring all the fantastic contributions that previous work already had. And so that was one thing that really set. The other one was, the other argument was that our papers continue to be accepted and to be highly cited. So if they're accepted for publication and they're highly cited, then they cannot be wrong, you know? And this is scary too, because this means that people are going to accept fundamental flaws as long as the machine, the whole machinery of paper publication and citation and tenure continues to work the same way, and it does. So there's an element of intellectual honesty that is really, really important, which is if it's wrong, is wrong, and it doesn't matter if it gets accepted. I mean, the worst thing is actually to get a paper accepted and cited that you know is wrong. I mean, it's like, how do you feel as a scientist, right? It's not a good thing. And so I had very mild success, actually, in trying to get the. There are many exceptions, fortunately, of people who have been doing things properly. For sure, Imre Chisar, Prakash Narayan, many of these people, Mathieu Bloch, have used strong secrecy and based it on very, very sound mathematics. But you have to be careful when you look at the papers and you look at the results, because then there's the third danger is then that people say, okay, this is what information theory says, and so this is true for all practical systems and all secure systems. And I hear this a lot in the information theory community, and it's very dangerous too, because you have certain assumptions, and under these assumptions, Gaussian channel fading, blah blah. Under these assumptions, what you're saying is that with all those abstractions on your model, this is what your model is saying. And in this particular case of security, you have people in computer science and cryptography and that have been studying these problems for decades. And so you really have to reach out and talk with them and have an honest debate and understand how are they looking at these problems. They are very protective, because again, the same way information theorists are very protective of information theory, so cryptography people in computational theory or theory of computation are very protective about their territories as well. So you have to start engaging in this dialogue. And so what happened was, though, that information theorists, when I talked with several of our colleagues and I asked, so are you talking with cryptographers? What do they say about weak secrecy? Because they all say no way, ever. And the argument I got from information theorists was, oh, they're doing their own thing and we'll do our own thing. So there was no dialogue. And so the reason I'm telling you all of this is because I think you're exactly at the right moment or defining moment of your of who you are going to be as scientists. And I think that the highest you can hope for is to be intellectually honest, and that means also sometimes not getting that paper or even retracting that paper or just realizing that it's wrong and correct it. That's the most important thing. And there are all these externalities that are influencing people in making the wrong calls and wrong decisions when it gets about and science is about discovering the truth, or at least coming as close as you can to it. So that's why I'm telling you this story. And for me, it was defining. I actually had quite a bit of a depression around this whole issue over a few years.
Sorry.
Yes.
Is it possible to concatenate the weak secrecy system with a 1 plus epsilon code, secrecy code, and make it a strong secret?
Is it possible to
concatenate with a very a code which is very close to grade 1 and make it a strong secret? In the sense that if you are the bits that are exposed are actually sublinear, and I assume a code with a very low rate would be able to solve that.
So what you're saying is that if I'm designing a code that comes very, very close to the capacity between...
No, to rate 1.
To rate 1, okay.
So you concatenate it with a rate 1 kind of secrecy code.
Mm-hmm.
So I assume you could be able to protect those sublinear bits.
Mm-hmm. Right. So no, I do think...
Easy. I think it's very easy, Barish, to go from the weak secrecy to something with a code which is very...
Right, but those codes are hard to design, right?
So I'm saying the results are not actually useless.
For the weak secrecy? So here's why. So you could. So let's say. What does it mean to be useful or useless? If you compute a secrecy capacity and you say the fundamental limit of secure communication over this channel is this is CS, okay, and you say that that's the fundamental limit, but then your criteria is wrong, then the result is useless because it's not it's not the fundamental limit of that channel, because it is probably going to be lower than that, because your security criterion is not, actually for the discrete memberless channel, actually the value of the secrecy capacity is the same. This is not true for other channels and multi-user channels, for example. Okay. So, so it depends on what you are saying how do you interpret the results. I haven't found this notion of secrecy very useful, to be honest.
João?
All right, so we have, yes?
Just one. There is actually another, even more, even stronger notion of secrecy, which is, well, I don't know how it is. I know it only for the discrete case. But if you look at the distribution of messages from Eve's point of view, when you look at the coordinate positions that Eve has access to, that distribution is in a one norm very close to the uniform distribution.
So Mathieu has a beautiful, and maybe there are other authors that I'm not aware of, but Mathieu Bloch did actually a whole paper on the taxonomy of conditions, where he also looked at the Kublai-Leibler distance between the distribution of the cryptogram and the message, and look at a bunch of different types of norms. And he actually ranked them. So this is stronger than this is stronger than this, and how it affects the capacity results.
But the point is that in the other case, you can't get to capacitive linear codes. You actually need very high denominator.
Good. That's great to know. Okay. All right. So we're supposed to stop at 12, so in 5 minutes, right? Yeah. So before starting a new topic, I'll leave the last 5 minutes for questions that you might have on all sorts of things. So Q&A, up to you. So who has a question? You all want to go to lunch. But I am not going to let you. Yes, thank you.
I have one in terms of what he asked. Because I think what he meant is that, precisely, if he makes an article showing that you could get this weak version, and you can add just a little bit more, and you'll get it to satisfy the strong version, then what he was saying is that then all the research done on the weak version is not going to be useless. I mean,
essentially what I wanted to say is that weak secrecy is a weak secrecy. I don't think that it's easy as concatenating a code, going from weak secrecy to a strong secrecy. But you have a notion of secrecy that can be, quite, I see it exactly like the outage thing. Because you're saying it 10% of the time, you don't get any, you're actually compromised.
But you're not, so the thing is that you're not really quantifying, so it's different when you say, when you compute an outage probability, by calling it outage probability and computing it, you're actually saying exactly.
So
what
here
it
I
is.
say that the outage probability is actually going to 0, but not fast enough.
So let me phrase this way. I haven't found examples of where weak secrecy is a useful notion to compute the fundamental limits of secure communications of certain channels, but I am open to evidence otherwise. So if someone is able to show that it's useful for some, then I'm the first one to cheer. What I feel very dangerous is when information theorists come and say, this is the secrecy capacity of wireless channels, and this is how many bits you can transmit securely, and do not say under this and this and this and this and this and this assumption. So that's what I find dangerous. Any more questions? All right, if not, then we'll see each other tomorrow afternoon. I'm looking forward. Take care. Enjoy.